basically roll a die locally, in a sense. And if their die came up with a good enough number based on what their stake was, then they can produce that block. And so what happens here is that, you get all these different forks where different people won different blocks. And if you notice, unlike BFT, we have a situation that's more similar to proof of work, where you can have multiple blocks being produced by different people at the same time because they both won the lottery. And in fact, in Ouroboros, it's very possible, more so than with proof of work, that you have like 4 or 5 blocks that all won the same slot, or perhaps slots where nobody won blocks, right? And so what this creates, in a sense, is a very forky network, right? We're going to keep on branching because different people have seen the blocks at different points in time, okay? This is the reason why probability, you were asking before about probability in Ouroboros, this is why probabilistic finality in Ouroboros tends to be longer than in regular Nakamoto consensus. In addition to that, we also have to think about some really unique problems in this kind of world, because in proof of work, there's nothing I can do inside of a block to increase my chance to win a future block. But in proof of stake, there is. In proof of stake, if I censor other people's transactions, if I ignore Coinbase's other people got, like I choose a transaction history that didn't involve any of these people, and then I give myself a Coinbase, and then I give myself another Coinbase, I can basically get a denser and denser chain over time because I'm collecting all the stake in the network, okay? It creates the situation that we call a long fork attack. In other words, if the network runs for like a year or two, you get in a situation where somebody could always start back at Genesis and grind out a chain that is longer, is better than the best chain the honest chain people are actually working on. Because what I've done is I've ignored all the Coinbases they've gotten, and all I've done is create a long side chain for years that basically has accumulated a lot of stake in my account only, and now I control such a large portion of the network that I can produce blocks more densely than the honest portion of the network can. And so eventually I can beat the longest chain rule. And so Ouroboros captures a variety of metrics within the blocks, or rather, let me be specific. Ouroboros, the way Ouroboros solves this is, I'll draw this again real quick. You don't have to stop the camera. I'm going to draw that long fork scenario, because the idea is, starting back at Genesis, the honest chain is going to look like this. It's going to be relatively sparse. It's just too big. I usually have a bigger whiteboard. Let me just do it with dots. The honest chain down here at the bottom is going to have kind of a sparse layout for a long time. And the dishonest chain is going to be really sparse at the beginning because I didn't have much stake, but then it quickly starts to get really dense. And so the way that Ouroboros solves this problem is you go all the way back where these two chains forked right here, and you're basically sampling this period of time, and you're saying, well, look at this. This was not very dense at the beginning, so I believe this is a manipulated chain. In other words, you're not just caring about the longest chain rule, you're also caring about the density, okay? Ouroboros requires you to look back at history to do this, though. So what we did is we adapted this into another adaptation on top of Ouroboros called Ouroboros Samasica that adapts this concept into the succinct setting, where we basically have a metric that we store in the chain called the minimum window density. That's basically, what is the minimum density ever achieved by this chain? If you're looking now at this one over here, the metric for how dense this chain was at any point in time in the past, the minimum density it ever had, is going to be worse than this chain, and that's more important than the length of the blocks. There's a few other metrics involved here too. There's actually a lot of other stuff here, like there's a short fork attack where you do something very similar, where you manipulate like the seed of randomness people are using to actually figure out whether or not they win, because there's like a random seed that has to go into every single slot check. And so there's a whole bunch of like metrics and properties that are encapsulated inside of every block in Ouroboros that you can use to compare blocks. So it becomes a lot more complicated than the longest chain rule, but you get the same concept in a sense. You sort of have the longest chain rule, but you have some additional checks to it as well to make sure that the chain's not manipulated in some bad way. What you're left with, oh, go ahead.
May I ask, when the soft fork, when multiple forks happen, what happens to the Stargate place?
Every fork has its own queue. When I'm operating on the Stargate place, I'm doing the same operation every block producer is doing, where I'm determining what the best block is, and I'm working off of that as the most recent state. So Some snark workers might be on those little forks for a bit, but then will converge back to the main chain. Sometimes those works will still be relevant. Maybe the transactions are the same. Sometimes they won't be. But the idea is that you're always tracking the best block you've seen so far and working off of that. Because every block has its own queue of work, every block I'm looking at is the state that I'm currently going to produce work for. Does that make sense? So what you're left with here is you get this really simple binary selection rule, where if you look at any two blocks on the network, if you know those blocks are valid, I can just look at some header information of those blocks, a few fields, and very quickly, very, very cheap operation, just figure out which of the two blocks is the stronger block. And just a quick mathy thing, the selection rule forms a lattice, which basically is just a fancy way of saying if I have a group of blocks, I always know that one of them is the strongest of that group, okay? There's no ambiguity. And so what you're left with is a situation where if I go to the network, right, let's say I'm in light node, I'm not listening to blocks on the network. I still have to sort of, in a sense, there's this trust problem, right? How do I know they didn't just serve me a bad block? If I query n nodes in the network, as long as one of those n nodes is honest, I know what the best block is. In other words, I'm not even relying on 51% honesty for that. I just need one out of whatever my sample size is. If I ask 20 nodes in the network, 20 different validators or, node operators for the best block, as long as one of them was honest about what the best block was and told me the truth, then I'll be able to know that that is actually the best block. I can verify each of the proofs of those blocks, which is proving all of this consensus information, like the density of the chain and whether or not each of these blocks was actually produced by somebody who was allowed to win that slot. And all that information is encapsulated in there. Once I verified those blocks, I know exactly which of the set of blocks is the strongest.
Could you like run out what are those headers information that the best block looks at? This minimum density is the block producer in there? Anything that you remember off the top of your head?
Yeah, it's a long list. Also,
more about it. Is there any risks that there still haven't been there can be still potential?
No, there's no risks.
Vector attacks.
There's no risks. All the attacks are actually mathematically proven in the Ouroboros paper to not be possible with the metrics they're looking at. It's one cool thing about Ouroboros is maybe this is not still true. It has been true as of a few years ago. I think it's still true though. Ouroboros is the only mathematically proven proof of stake protocol.
Oh, probably.
So there are. Don't try and read the proofs. I don't recommend it. The proofs are awful to read. They're really horrible, but they have been verified by universities and by our own PhD that we had hired in the past to verify the proofs as well. And they've actually found some mistakes in the proofs. Right. But it turns out the proofs are still valid. There was just some intermediate mistakes and they could still be proven. So it's the only mathematically proven protocol. So there are no gaps. In fact, the proofs are so detailed that they're even considering parameters around network delay and attackers using network delay and taking nodes offline. There's actually a lot of detail in the proofs. It's very impressive how detailed they went.
Do you mean that other yellow papers or white papers are just built their system like they can't break it somehow?
Yes. No, this is true.
Okay.
It's like, hey, does anybody know how to break this? They're like, I don't see a way. But to be fair, like with BFT, you kind of can't mathematically prove it. It's sort of based on properties of how BFT works that you sort of buy into. Because this is all entirely based on probabilities, because it comes down to Nakamoto consensus, which is a probabilistic consensus mechanism, you can basically prove that there's this overwhelming probability that nobody can ever cheat it. That's essentially what the proofs boil down to. It just becomes a really complicated version of that. They consider short fork attacks and long fork attacks as two different categories of attacks that can happen on the chain. And then they mathematically prove that those attacks cannot be executed with very specific setup of those metrics. And there's a lot of detail to them. There's like, you separate things in epochs. Epochs set up VRF seeds. There's different checkpoints in which the VRF seed is computed and then has to be frozen before the next round of epochs can happen. There's like the staking ledger and there's the next staking ledger that are like two epochs apart from each other. So there's a period of time where the network has to settle and finalize what the actual staking distribution is. There's like all of these checkpoints and logical like things you have to do in Ouroboros. It's a very complicated consensus mechanism to implement. But in the end, it gives you all these properties, basically. So, and we implemented a snark group, which is super useful.
I think I miss something, but I'm wondering just how exactly does the one of n, one honest actor out of n work? Is it simply going through the heuristics for verification, like density, minimum density, or are there other factors there?
So there's a binary selection rule. Basically, given any two block headers, I know which of those two block headers is stronger than the other. And so using that rule, I look at two blocks and I'm like, okay, this is the stronger of these two blocks. You can extend that where you have n blocks. You just sort of keep on doing that operation, folding over them all. It's like, oh, this is the best one so far. Is the next one better? Oh, no. Okay. Is the next one better? Oh, this one is better. And you keep on doing that. And you basically, it's a max operation. Like if I have n blocks, I can figure out what the max block is, the max strength block is, in a sense, from those. That's what I meant when I said a lattice before. It's like just the way of describing that concept that, like, given a set of things that have some comparison operation, I can find the max item from that list. Does that answer it? And then block header is attested to by the proof. So we know that the contents of the block header, all the metrics encapsulated, are correct and have been computed correctly forever via the recursion clue. And then we're just comparing those metrics, basically.
The slot times are 3 minutes
Right now.
and can does that affect performance of Mina? And can that be reduced? What's the logic behind making it 3 minutes?
So originally, when we launched mainnet, we made it 3 minutes because it took 2.5 minutes to produce a blockchain proof. But that's not true anymore. Now you can produce a blockchain proof in about 10 seconds. So the only reason it's 3 minutes still with the Berkeley launch is because we didn't want to put too much risk in changing too many things about the chain for Berkeley. It's already such a large upgrade. The next hard fork, we're going to dramatically reduce it. And I think in future hard forks, we're going to be dramatically reducing it too. We plan to reduce it at least to 30 seconds. I think we can even do better than 30 seconds. We've tested it and had success at 20-second block times.
Does it make it faster?
It makes finality faster. It makes transaction throughput faster because we're not decreasing the number of transactions you can have in a block. We're just decreasing the time per block. And so, yeah, it does heavily scale the blockchain to reduce that.
The reward distribution time will be shrink somehow, right?
Yes.
And if it is still kept manually, wouldn't be a burden for validators to distribute the rewards.
So I didn't understand.
Imagine that you make the block times like 20 seconds, then what it makes each epoch? 1 day?
I need to do the math.
Less than a month.
Yeah.
Less than 14 days at least. So a validator is supposed to manually distribute rewards.
Yeah.
Once a 2 day, right? Wouldn't be a burden for validators?
I mean, it's sort of the same burden they have now. It's just sped up. The transaction throughput is higher now. So it's the same operation, the same cost to do it, but the operation can happen faster in the network now. I will mention that one of the things we're planning to do in the future, I just don't know exactly when, is provide a zkApp for actually doing integrate the validator pooling logic into a zkApp so that instead of the validators having to do these manual payouts, they'll basically collect information on chain that can be used for people to come and withdraw their claims from that zkApp. That's also better for tax purposes for people too. So.
Yeah, I kind of wanted to ask about that because, many other blockchains have their staking, the liquid staking. Mina staking still is pretty decent per se, but then I always had that feel that as in the stake payouts done within the protocol somehow. Could that be ever possible, or you would look at the other zkApp solution like what you just mentioned? Why would it never been embedded within the protocol, make those payouts?
Working with that zkApp would be embedded in the protocol.
Okay.
So it will be embedded in the protocol. We can make it embedded in the protocol, and I think that's what we're going to require everybody to do. But zkApps is just the layer that we're going to push it to because it's the layer that makes sense to have this whole concept of like on-chain, you come and interact with just a regular zkApp to do your claim. Like don't create a second mechanism for claiming these rewards. Integrate it into the same layer that's like this programmability layer people can come and drop claims from. So in a sense, it's like a special zkApp that's baked into the protocol in some sense, but operates on the ledger like any other zkApp. This design is still like TBD, but I'm almost certain that's where we're headed.
Fair enough.
Okay, that's all I'm going to talk about consensus for now. I can go a lot deeper at consensus, but I'm not going to right now because it's really boring. So far what we've been doing is this entire time I've just been talking about payments, right? I've just been saying, hey, we're going to send 5 Mina from like account A to account B and talk about how we prove that. But now let's talk about how we're integrating that into a world where people are actually writing applications on the chain. So I'm going to redraw this whole thing. I'm going to redraw this whole thing. I wish I had one of those like paper things because I can go back and forth, but so far we've talked a lot about consensus and the state transition model and how we can take proofs from the state transition model and include them back up into the consensus layer and get that one big proof of both things. Each of these transactions we've been talking about so far are simple payments. They're following the simple circuit logic where it's like, there's a payment, I'm going to pay this person this amount of money, and that's projecting some changes into a ledger. Now we want to talk about applications, where these transactions are not just payments. These transactions are actually applications that are being executed. And in a sense, what we're doing, the really simple version, it's really simple, is we're just taking proofs that are off-chain, and we're including them into transactions, and then the transaction proof is verifying those proofs, right? That's the whole idea. It's basically the idea that users can now generate proofs. They can submit them into the transactions. This transaction is not just a payment anymore. This transaction is sort of anything based on what this proof is saying it should do. And then we're verifying that recursively in the state transition model, and then we're verifying that recursively in the consensus layer. And so we get this whole roll-up of all the user applications forever, right? So what does that actually look like? This is the thing I always struggle to talk about a little bit, but at a very high level, if the proofs are happening off-chain, right, we're not actually executing things on-chain. We don't know what the state is that this proof will be applied to, right? We have this problem where on like EVM, the execution and the state and the sequencing, they're all together, right? When a block producer sequences a transaction, it has the state that transaction can be applied to, it executes that transaction as code, and produces a new state. So the execution and sequencing are linked. In Mina, the sequencing, these two layers, is divorced from the execution. It means that when you're executing this proof here, you don't actually know the state that you're going to be applied to. Because of that, the way that we describe an application is, naively, let's just say that we wanted this app to do a state transition. It's just going from some state to another state. That's not really going to work, right? Instead, what we want the app to do is we want the app to have some preconditions, things that need to be true for this application to be processed, the update to be processed. And then if those preconditions hold, a series of updates to the chain. Okay? And we break these up into bundles. Basically, the way we do it, we try and draw it here, is like, let's take our same example of like sending 5 Mina from A to B. Okay, but now we're going to do it as an application, right? An application's controlling this transfer instead of just using a payment. So we're sending 5 Mina. The way we would encode this is, I'll talk about it as, I shouldn't do call stack now. I'll just say it like this. We basically have 2 different updates that happen, basically 2 different slots of things that are happening, sort of like side effects. We have one update that's saying subtract 5 from here, and one update that's saying add 5 to here. And to at least one of these updates, we need to attach a proof. Okay? And so each of these updates, literally what a zkApp transaction is, it's a list of what we call account updates. They don't always have to update something. They can also just look at the account state. And so each of these can have preconditions and then updates that are down to side effects and can have those preconditions and updates committed to in the proof. These are the public input to your proof, is the preconditions and updates that you're going to do. And so the chain is able to check, this proof is valid, and this proof is attesting that we need to subtract 5 from here, and we need to add 5 to here. And as part of that, it's saying that something has to be true about A. and something has to be true about B. Now we can actually look at things about A and B and say these have to hold preconditions. But we don't have to know the exact state of B or A. I don't have to say that I know that A has 5 tokens to send. I can just say that A has to have greater than or equal to 5 tokens, right? In other words, our application's not, the public input to the application proof is not the state that we're moving from and going to. The public input to the application proof is the list of constraints that can be checked on chain when it's sequenced that have to hold for this to succeed. And the chain is basically at the point it's including this in a transaction, deciding, is this good or is this failed? Okay? It checks these preconditions and determines whether or not this could actually be processed. So the zkApp off-chain is just attesting to the things that need to be true on-chain. When we sequence them, the proof for this transaction is checking that those preconditions held. I'm going to pause there, answer some questions, and then I'll move on. So anybody have questions about that?
Yeah, so, well, about that, but not about that exactly, because I always been confused. Why does the read of account makes account, within zkApp, it makes account update? Because it does, right?
What is what?
If you want to, if you are, okay, so if you are accessing another method of other smart contract that doesn't change its state, it just reads the state,
Yes.
It's still an account update.
It is. Also, you probably should be calling it method, but we'll talk about that later. That's a miscommunication in the design. Okay, but let me answer the first question here, which is, I actually am really trying to find out a new name for this. So if people come up with a name, let me know. Account update is not an update. An account update could contain an update, and that's a very confusing name.
Yes.
An account update is going to have optional preconditions and optional updates. In a sense, both of those are optional. They're not, neither is required, okay? The preconditions can be empty, the updates can be empty. That means that you can have an account update, which is just verifying the state of some other account. It's not changing anything. Account updates are not necessarily mutations. It's sort of a misnomer. Does that answer your question?
Verifiable query?
It's not really a query because you could be doing something too. A query implies like immutability.
What is query and mutation? What's a term above it?
That's the issue. I haven't come up with a good word for it yet. They're basically, the way I think about them, but this is a bad name, is they're like lookup slots. Okay? Every update in the list of updates is like saying, I'm going to look up this public key and I want to reason about it in some way. That could be me looking up that precondition there, like looking up the account and just checking a precondition. That could also be me like looking that up and just doing an update without checking the precondition, but usually it's both. Usually I'm going to look at it, like in this example, we were inspecting both, but let's say instead it wasn't this example, it wasn't A sending me 5 meter to B. What if A was a token contract and B was a token holder, and A is just wanting to check, like, if this thing is true on B, then like I'm going to mint tokens. There's a precondition on A that's checking some state on A that allows B to mint tokens, but there's no update actually happening in A necessarily.
Exactly my use case that I'm always confused about. So yeah, that account update.
Updates don't need to be up.
Yeah.
Yeah. Okay, so you were asking about why you don't need to call a smart contract method if you need to read. So I'm going to talk about the call stack in a moment, and that's going to make more sense about exactly what a method call is and why it exists. But first, let me just describe how you would do it without a method call, okay? Because a zkApp transaction is essentially a list of these, like whatever you want to call them, updates. Still keep on calling them account updates for now because it's the standard terminology, but each of these is basically a slot to look up an account in the ledger. So if we have a ledger over here, each of these can be looking at different accounts inside of this ledger and then reading the values. All of these are a read, period. Every single account update is going to read an account, regardless if we're doing anything to it. In that read, we're allowed to specify preconditions, which are things that have to be true when we read the account in order for the whole thing to apply. So if I want to read the state of another account, just to check if something's true about it, I don't actually need to call another method. I don't need to generate a second proof for that. The way that you usually do this is there's this concept of the call stack, which is basically, this is like a list of things, but what we do is we order them into trees. And what these trees are is these trees provide a parent-child relationship such that we could have a proof here that's looking at these two updates, where these two updates don't have proofs. So I could have one proof. Let's take the example where I was sending, let's go back to that example I had before. It's just the easy example of A sending 5 Mina to B, so we're subtracting 5 from here, and we're adding 5 to here. Okay, if I fill in a circle here, that means it has a proof with. I could do this in either order, but I'm just going to do it in this order, where I'm going to say, this account update here is for A, and says that we're going to subtract 5 from it. This account update for here is for B, and it's going to add 5 to it. This proof can inspect the children account updates that it has under it. So I only need one proof that's going to check this whole operation, but you create a parent-child relationship that says that this proof can look at its children. The way that you do this is actually this whole structure, we call it the call forest because it's a whole bunch of trees. But within each tree, I can basically keep on going down the tree as far as I want to, look at all the account updates as private inputs to this proof, and then hash them back up to get the root of that tree. And that's what my child actually is. The child is the root of my call stack. It's just a Merkle commitment to the account updates that are underneath me. So if I have one proof that wants to read another account, I don't need to call another method in the smart contract and generate a second proof for that. I can just literally look at that account in a child account update and then put a precondition in there or something. In other words, let's go back to the example where we're minting a token. Let's say that you could do it this way. I mean, this probably isn't the way you do it, but I just want to kind of hammer in the idea. You probably do it the opposite way. Let's say that I'm the token holder and I want to mint tokens. And so for me to mint tokens, I need to prove that the token contract allows me to mint tokens. And maybe this is as simple as just checking some state field on here. Okay? I don't need to call a method into the token contract to do this. All I have to do is just push an update that has a precondition on the token contract that's checking the state. And then I'm able to mint up here. But I could generate the proof from the holder. Usually you probably reverse this. Usually you want to have the token contract have all the contract codes, so you probably actually do this in the opposite order. But the point I'm trying to drill in here is that when I want to look at multiple accounts in the ledger, I don't have to generate proofs for all those. I don't have to have them all be contracts. I don't even have to know about the contract code. I just have to know about what kind of precondition I need to make on that other account in the ledger. And then I can push that into my call stack and inspect it for my proof.
Then to solidify, if I have a zkApp with states and my methods that doesn't have any get assertions, but only do set and maybe assert bigger than, I don't know, then that wouldn't cause any concurrency issue, you say?
If you're only setting and not reading states, there's no concurrency issue because you're just overriding all your states. I mean, you are creating a concurrency issue in a sense because you don't know what the ordering is going to be and you don't know if the transitions are valid.
And that can be changed till the hard finality, right? The final state.
I don't quite understand.
If the operations are not commutative, then till the hard finality, the order that they're executed can be changed.
Yes.
So basically there's a difference between writing get and require equals a state and then assert something and directly asserting while, at the beginning without actually getting anything.
Yes. If you don't do the required equals, you're not making a precondition.
And would it be possible theoretically to write a code that executes something conditionally without knowing the condition? Like, can I say if A has bigger than 5 pounds, transfer all of them to B? I don't know the state, but I need to know the state to execute the transaction. Can I write?
That is what preconditions are for. Now, what you can't do right now easily is have an else clause. Like, if that's not true, then do this. But if you want to predicate some update happening, that's exactly what preconditions are for. Preconditions are saying, this thing has to be true for this update to happen. The update won't happen if the preconditions don't match.
But can I make the update depend on the current state without knowing the state?
Yes, that's what preconditions are. preconditions are not a commitment to the state. They're a commitment to a condition on the state. Now, you're limited in what you can do. You can only do equals, greater than equals, less than, or less than and equals. Those are the 5 operations that you get in your preconditions. So depending on how your state's represented, you might be exactly in that situation. Like if you have a Merkle tree that's committed to in a state field, you're basically stuck reasoning about that exact state.